Now, before we get into example 3, we noticed that from the warm-up example 1 and example 2 that we had this exact same binomial, this x squared plus 1, and that we kept raising that exponent higher and higher and higher. And as a result of that, we saw that we ended up with more and more distributing to then be able to take the derivative. Now, when we go back to the, this was example 2, if this wasn't, say, for example, 4, if this number, this exponent was not 4, we might have some other number like 100. And can you imagine trying to actually, essentially distribute and distribute and distribute and distribute 100 times to then be able to take the derivative? That would be a lot of work. And as a result, we wouldn't want to come up with something that's going to really help us out when we have these really high order exponents. Now let's just imagine for a second that g of x is equal to this inside part, and that f of x was pretty much that exponent on the outside. It's x raised to that 4th power. Then the composition of f of g of x would be anywhere that there is an x, we're going to throw inside our g function. So that would be x squared plus 1 raised then with all those numbers on the outside of our f function, that would be raised to the 4th power. So really, this is the composition of our two functions, f and g of x. And then you could go ahead and take the derivative with respect to x. And we actually saw that when we were looking at examples 1 and 2 and even the warm-up. Now, how the chain rule actually works is, in that event, if you're trying to take the derivative with respect to x of f of g of x, the chain rule says that you're going to take the derivative of the outside most function, in this case it would be f, leave the inside function just as he is, so we'd still have g of x. So again, we just took the derivative of the outside function, we rewrote the inside function, and then we're going to multiply this by the derivative of our inside function. Chain rule, you're actually going from the outside in and taking derivatives. Now, for example 3, how that's actually helping us out is determine the inner and outer pieces of the following composition of functions. Well, for this first one, y is equal to 1 over x, the inside function would actually be the x plus 1. And it's extremely subtle here, but you can imagine that this x plus 1 is in fact the inside part of that function. Now the outside function would be considered to be 1 over x. Because again, you could literally take this inside function, throw it in anywhere that there is an x inside the outer function. You could also rewrite this as this x plus 1 raised to the 1st power, and we've seen where we've taken this bottom piece and thrown it up top, to then have x plus 1 raised to the negative 1st. And as a result, this part would be considered your inside function. So there is the inside function. And x to the negative 1 would be considered our outside function, because there's our exponent. So these are in fact equivalent to one another though. Now when we're looking at the sign of 2x, our outside most function would be the sine of x. Our inside function would be this 2x. So pretty much anywhere that there was an x, we would throw in that 2x, and then you could see that composition of the functions. For the tangent squared of x, well, the tangent squared of x is literally the same thing as saying the tangent of x quantity squared, and as a result, the inside most function would be the tangent of x, and your outside function would be x squared, because you would literally take your inside function, tan x, throw it in anywhere that there's an x, and then there's your composition of the functions. Now with the chain rule, it's going to save you an incredible amount of time, especially because you might have some polynomial with a very, very high degree. And as a result, you'll see then why that chain rule is so important to know. But again, that is example 3, and looking and seeing how the chain rule actually is operated from our 2.5 set of notes.